Hi everyone, welcome to another NOVE event. And for those of you joining us for the first time, we are the Neural Engineering Research Venture, and our aim is to bring neuroscience to life in Africa and around the world. My name is Julianne, and I will be your host for the evening. And then my colleagues Darby and Siobhan will be lurking in the comments. Then today, in the spotlight, we have a mention of the Indaba X Roadshow for 2021. So the roadshow, or the Indaba X, is being held in the form of a roadshow this year, and it started on the 3rd of September and is currently taking place. Each event is hosted by a different team of local organizers and institutions, and the next event will be held this Friday, the 15th of October, and it will be hosted by Data Profit. So be sure to take a look at the website for more information on the upcoming events. There I have some of the dates, and I will share the link for you in the comment section. Then, just a couple of house rules. Please do use respectful and inclusive language on our platform. And remember to post your questions in the Ask a Question feature. So you can also vote for your favorite questions there. We will change the format up a little bit tonight. So you can post your questions as they pop up, and then I will ask our speaker to answer them as we go. Otherwise, you can just post them after the talk and we will get to them during the Q&A. Then if you don't have a mic, don't worry about it. We can ask the questions on your behalf. Just remember to add please ask. If you don't add please ask to your question, we will assume that you will be coming on screen to ask. Then, if your connection is slow, try to refresh your browser. Alternatively, you can select the compatibility mode in the audiovisual help button and just change your settings there. But if your connection fails completely, the talk will be available to stream after the event. Then we are very excited today to be celebrating Ada Lovelace Day. Ada Lovelace was an English mathematician and writer who worked together with Charles Babbage on the analytical engine. She is often regarded as the world's first computer programmer. And Ada Lovelace Day is an international celebration of achievements of women in science, technology, engineering, and maths. It aims to increase the profile of women in STEM, to encourage more girls to pursue careers in STEM, and to support women already working in the STEM environment. And NOVE is very proud to share in this mission. Then I'm also very excited to be introducing our speaker for today. Emily Muller is a PhD student at Imperial College London, and she's currently doing an internship at Accenture. Emily is primarily interested in applying the power of machine learning and social science to understanding our surroundings. She is also an active member of the African deep learning community, and we are especially excited to have her join us today. So with that, I will now hand over to Emily to share her screen.
Thank you so much. All right, thank you for having me. So is my screen visible?
Not yet.
Not yet.
There we go.
Awesome. All right, thank you everybody for being here and joining me. It's not quite neuroscience, but it's not too difficult a conceptual jump from neuroscience and computer vision for the urban environment. Today I'm going to be talking about some of the work that I've been involved in through my position as a research assistant and currently in my PhD on using images to understand the urban environment. So, let's see. So thank you for the introduction. So as we mentioned, I'm currently a PhD student. I like to call the intersection of what I'm doing computer vision and urban analytics. I kind of got into this role from working as a research assistant on a project called Pathways to Equitable Healthy Cities, cross-institutional collaboration, looking at measurement in different urban areas. So lots of focus on air pollution, noise pollution, walkability, and the two projects that I was involved on, which I will touch on later just briefly, were transferability. So how well can you learn prediction labels from one city and transfer those to another city using street view imagery? And the other project that I was involved in was looking at predicting pollution levels using street view imagery in Accra, Ghana. And then the research that I'm doing, which I'll jump into after this slide. And just a side note, I'm currently working on synthetic data generation on a 6-month internship before going back to my PhD, which obviously doesn't exist, it always exists. So there's no going back, I guess, it's just a continuation. And MRC, Centre for Environmental Health, are my funders, and this is a centre across Imperial and King's College, all interested in measurement of environmental hazards. So what was the motivation sort of for my research, and how did I get involved in the work that I'm doing? So in our group, Ezra Sewell in 2019 did a wonderful paper looking at predicting socioeconomic indicators in London using street level images. So with Google Street View, she scraped probably, I think, close to 100,000 images and 4 different angles. So it's a 360 image, so you can choose each of the different angles. And she was able to get a network which had a mean absolute error of ±1. So essentially, if the income decile was, let's say, 7, the model's predicting 6 or 8. So this work sort of paved a way for showing how socioeconomic variables could be measured at higher spatial resolution and also at greater temporal frequency. Because typically the outcomes that were being used for prediction, so such as income and education, were from census or surveys. And the problem with surveys is that either they're not entirely complete or they're very expensive. And of course with census, they're very complete, but they're done quite infrequently. In the UK, it's every 10 years. From the substantive side, sort of some of the limitations around surveys, whereas with this work, some of the limitations with this work in particular were, so it was a black blocked model. She used VGG-net with 4 different inputs. So there was really no understanding. As you can see here, there's like low predictions of unemployment, whereas here very high. There was no interpretability of why these images were being predicted high or low for each of the outcomes. And then on top of that, the level at which the predictions were taking place were at something called the LSOA. So this is sort of equivalent to enumeration area in South Africa. And it's essentially a group of, let's say, 1,000 homes, and it's the average household income or self-reported health within that area. So another motivation was to say, okay, is there a way of getting individual image level labels that were actually interpretable? And so my approach was to say, okay, can we cluster? Instead of doing supervised learning, can we do unsupervised learning to come up with some sort of interpretable clusters within the city? And why London? So aside from the fact that I was living here and I was actively experiencing the sort of visual information which is indicative of certain neighbourhood environments, there is also objectively a lot of heterogeneity within London. And if any of you have ever been here, you kind of notice or live here, from one street to another street, you can feel like you're in a totally different place. And you can see, sorry, this is a bit blurry, the resolution's lost a bit. You can see there's very discrete spatial patterns where it's high and low income. And one of my colleagues, Theo, who's a PhD candidate, has been looking at modeling of life expectancy using health data. So the correlation with, you can see, this is, for example, where Imperial College campus is, which is South Kensington, Chelsea, very high life expectancy. And there's a correlation here with income. So the heterogeneity of socioeconomic outcomes is directly related to health outcomes in London in particular. And so I mentioned previously this level of LSOA, which there should be about 5,000 of those in London. And I've just given an illustrative example of the delineation of what an LSOA is. And this is an example of the types of built environment which are included in one given LSOA. So it can be things which you would a priori think have a very different socioeconomic indicator. And again, here's another example where on either side of the street, the homes essentially look almost identical, but they're considered 2 different outcome levels. And here are just a few examples of Google Street View images that are taken from 2018, just so you can get an idea of the sort of angle that's being captured and the information which is included in these images. So one of the not so benevolently good things about my research is that the Google Street View car has been actively collecting information in London since 2008. So there's probably 5 million or so images in total that exist capturing the urban environment in London. And I was trying to capture a way of I was trying to measure a way of seeing, well, how continuous are these images in actually getting the whole city. So the dark green points underneath represent all of the roads in London sampled at 20 meters. And on top of that, the light green actually show where the exact images are. So you can see that there's some spatial missingness, and this happens year on year on year. But essentially for 2018, which is the year shown, 70% of the roads are covered by images. So, and I did this by matching it to each of the sample points from the road. So there is quite high spatial continuity, assuming that 20 meters is sufficient to cover one spatial area. So the crux of it really is to ask, how can I meaningfully extract information from imagery from clustering? And I sort of broke it down into these two different strands and two different ways of going about it, which is two-step. First of all, feature extraction, how to get relevant information from the images in a reduced way that can then be used as input for a subsequent clustering method. Or the other option is end-to-end. So there's various different deep clustering models which consider also a cluster loss in the training paradigm. So I've continued with this original method at the top. This is called RMAC, Regional Maximum Activation Convolution Network, and essentially it uses the VGG feature extraction pre-trained on ImageNet, but instead of just extracting the 512 I've forgotten which layer it is, 11th layer, there's also this regional pooling which takes place. And essentially what this does is it provides summaries of separate regions, which actually starts to give information about distinct objects in the image. So it takes what would be a global feature extraction method with the input and straight to the output of this 512 vector. It actually then becomes localized by having these interesting regions, and also really good for the work that I'm doing because the images are quite consistent. You know, the pavement's always on the bottom, the houses are always in the middle, and the sky's always on the top. So the regions are actually meaningful across the entire sample. Okay, so this is just an illustration of how to choose. So for the method before, I said two steps. So the next clustering methods, I had a look at a whole bunch of different clustering methods to end up settling with k-means, which was I was quite happy about that, to be honest with you. But just in terms of scalability, and there was a bunch of other reasons why k-means was a good clustering method to choose, which I don't recall right now. But the problem is choosing, how to choose number of k. So there's various different metrics, which are like model internal metrics, which are used to optimize separability and betweenness. And based on sort of maximizing the silhouette score and minimizing this David-Walden index, which I won't go into exactly what they're measuring, I chose to look at k equals 9 and k equals 20 as two different groupings of clusters for the images that I had. So here's just uninterpretable visual splattering of the 20 clusters that exist in London. You can see already there's slight grouping, spatial grouping, and especially because of that color red, you can see it more. But I'm going to go into how I've sort of interpreted and named and labeled the clusters thus far. So the goal of interpreting clusters is just typically a very difficult problem with unsupervised, or difficult issue with unsupervised clustering. So I've sort of looked at these different ways of making sense of the clusters, which is to say visual inspection. Okay, what do they look like when we look at all of the images which are labeled as cluster A? What is the spatial distribution, and how do they correlate with features from imagery? So that is the objects which have been detected and the semantic segmentation, and also external features. So before sort of throwing all of the objects and segmentation features into this interpretability process, I've said which ones are the most important for predicting. So I just built a classification model for the 20 clusters, and I wanted to predict cluster assignment using the segmentation proportions and the object counts. So from that, I've got a list of 9 of the most important features for predicting cluster assignment, and the accuracy of the model ends up being 46%, which is not great, but a lot better than the 5% which is expected when from random allocation. So I'll take you through sort of the thinking behind it. There's quite a lot of information here, so I'll go through it kind of slowly. So first of all, the white titles is what I've called the clusters based on this analysis. So I'll start here at the bottom, and the bottom left, there's this commercial cluster. So the spatial distribution, if you look sort of at the other maps, there's this very strong attachment, I want to say, but that's not the right word, pattern along these arterial networks, and especially in central London. And it's virtually the only cluster which shows any appearance of people within the image. So this, and furthermore, lots of building is present, hardly any greenery is present, and there's also a lot of road. So sort of densely packed buildings quite close to the road itself are indicative of this commercial cluster. Then if we look at the top, terrace residential, this is very, very typical London style of housing, spread all over the city, not so much in the centre. There's high proportions of sky, given that the terrace just continues along this line, and equally with the equal amount of building. Not as much vegetation, but all of a sudden we're seeing more cars because of roadside parking being more common with terrace residentials. So high density estate, characterized by, again, a lot of sky, less building, but importantly, there's also this vegetation which appears. And this is also very typical London sort of architecture, is estates which are situated sort of not directly on the road, but placed further back on the road with a green sort of terrace in front of it, or vegetation in front of it. So that's an example of high density estate. Let me go over to this side. So interestingly, with these 3, I was seeing, so residential fringe, like all of them sort of live on this green belt of London. So further towards the periphery of the city. And I was noticing that for residential fringe parked cars and road parking, there was a lot of segmentation of car. So there was a lot of object counts of cars. So here you can see residential road parking, object counts is virtually the same as residential fringe park cars. So essentially quite similar in terms of objects. However, with segmentation, the lower cluster has a lot more pixels which are related to cars. And then by visually inspecting, I've seen actually this bottom cluster is representing cars that are parked on the road. That's closer to the Google Street View camera, as opposed to the cluster above, where the car's actually situated in the driveway. So that's how I've then differentiated between there being a driveway in these properties as opposed to roadside parking in these properties. And I've eventually grouped these 2 clusters together because they've got a very similar, let me call it, fingerprint of the features which are extracted. And the next set of clusters is much more related to greenery and roads. You can see here, especially in these two clusters, there's a lot of following. Here we were seeing like centralized roads, which are indicative of a lot of high streets, sort of centers of town within London. Whereas here we're just seeing a lot more roads in the outskirts of London and huge amounts of green present. So this non-residential green roads, there's a lot of vegetation present, and similarly non-residential roads. These, again, very similar fingerprints. I've grouped them together, and slightly less interesting clusters over here, so I won't go through all of them. But just so you get an idea of what I was talking about previously, so on the left is the terrace residential housing, very typical of London. On the right, high density estates, typically red brick buildings, quite similar patterns of windows continuously, high density or medium density. With the examples that I was speaking about earlier, residential fringe driveway cars, you can see the cars are parked basically perpendicular to the image itself, whereas residential fringe, even though they do have driveways, the cars aren't parked. So it also starts to raise questions about given that the images are just taking it one time shot, I don't have, very, very frequent temporal images to say what happens in, day after day after day. What sort of conclusions can be drawn from, for example, the distinction between there being cars parked or not parked. And then roadside parking, as you can see, which is quite evident, and this is just an example of this sort of leafy residential suburban life on the outskirts of London. High density modern, more examples, and commercial. So commercial is typically characterized by the bottom floor, the ground floor of all of the buildings having some kind of different pattern and suggesting that there's actually retail happening in these buildings. Of course, the clusters are not perfect, and k-means is a sort of method which doesn't give you this probabilistic output, as opposed to methods that do, but are much more difficult to scale on the number of images. So I think for the number of images that I had is 1.2 million. So as I mentioned before, k-means was a really good method to actually scale for that number of images. And then, so these are all the 20 of them, and I just wanted to highlight that I actually removed 4 of them just because of the angle at which the image was taken. So the way that I downloaded all of them, I wanted to get images which face the building facade, as opposed to images which face the road, because I wasn't so interested in what the road says, but actually what the building itself is telling us about that neighborhood. So 4 of them are image artifacts, which I didn't want to be in the collection process in the first place. So from 20 clusters, I was able to reduce it down to 14, 4 of which were image artifacts, as I've mentioned, and 2 which I grouped together. And the 2 which I grouped together, so let's say it's this star here and this star here, cluster 6 and cluster 1, they actually come from the same parent cluster when looking at k equals 9. And similarly, the other 2 clusters, which is 8 and 9, they come from the same parent cluster when choosing a lower number of k. So 9 out of the 14 are descriptive of the built environment, and 5 out of the 14 are descriptive of the road. And the next sort of question I had is, well, how do these relate to census statistics and levels of pollution? So in 2014, I think, Singleton and Longley did something actually not so dissimilar from what I'm doing, but not with images, with census statistics. So I previously mentioned lower super output area, which is about 1,000 homes. They use output area, which is about 70 homes, and there should be about 50,000 of these in London. And they've taken all the census statistics from each of these output areas, and they've clustered them into different groups, and then given each of the clusters categorizations. So on the left-hand side here, you can see the different categorizations that they've given are not quite home counties, city central, East End Asians, etc., etc. And this is just a visual depiction of subset of those, so only 7 of those, because again, it's quite difficult to visualize on a map the full distribution of the clusters. So what I've done is looked at what proportion of the clusters, what proportion of images are found in each of those output areas, and to then glean some understanding of the visual makeup of each of their clusters. So for example, not quite home counties. So this is like a really English expression, and essentially it means this outer part of London, which is not quite the home counties, which are these very wealthy sort of outer London elites, I would say. So they have this title, not quite home counties, and typically from the clusters, and this is coloured in green in this map. So this is this outer green area, and just below is detached retirement, which is this blue area here. So slightly less southeast, but very similar spatial makeup. So the majority of these are made up from residential fringe, unsurprisingly. Slightly less residential fringe in the detached retirement as leafy residential. So then moving further down, looking at educational advantage, which is this sort of light green. So education, all of these 4 here that have the dots next to them occur quite centrally in London in quite a similar spatial location. So we've got educational advantage in the light green, which is made up here, as you can see. Which is made up a lot of commercial and high density modern. And this is there's also not very much high density estate within this educational advantage category. If you sort of go down and look at these other 3, which is students and minority mix, Bangladeshi enclaves, and disadvantaged diaspora, there's again a lot of high density modern, but what was previously commercial is sort of overtaken now by high density estate. And even though the spatial location is really quite similar, and this is something which is quite characteristic of the UK, not London in particular actually, the UK is estates being a place that typically house people that are on the lower end of the income spectrum. And obviously you can imagine the origin of estates was for social housing at one point in time, which it no longer is because a lot of them were sold off at some point in the 60s. So it's sort of now a mix, and it's less discrete as it would have been in a previous time, but there's also a lot of like stigma and sort of phrases and behaviors that are attached to the notion of estates for whatever reason. So that's just a little side tangential story about estates. And so for pollution, I was looking at the correlation with this Tranquil City Index, and this is done by a group called Tranquil City that are interested in giving ratings for how different locations are good for our well-being. The bars coloured in black are the clusters which are related to the road, as I mentioned before. So green roads, much higher, well, I wouldn't say much higher, but higher levels of tranquility than this commercial cluster at the bottom, which kind of matches what we would intuit as well. And from the perspective of housing, sort of leafy residential is on the highest end, and as I mentioned before, commercial and high density modern on the lower end of tranquility index. So this index uses a whole bunch of things, a lot of it's to do with sounds, pollution levels, land quality, land use, and all of those are kind of included to come up with an index. So for this part of my research, I want to look at how things are changing over time. There's a lot of different avenues, which is exciting and overwhelming simultaneously. But to look at, first of all, how do neighborhoods change over time? So because Google Street View Car has been around for a long time, it's possible to look at census statistics from 2011, which was the last time the census was done in the UK, and fingers crossed 2021 as soon as they're released, and how the images are actually relating to changes in socioeconomic indicators. And then also, rather than looking at the Singleton and Longley work, which I pointed out, to look at unclustered census statistics, and probably also at King's, which is actually now Imperial, the Environmental Research Group, have really good maps on pollution in London, so to actually use raw pollution levels as opposed to the Tranquility Index. So I've just seen there's some questions here, which are, do I use R? I haven't used R in a while, actually. So that was from Simisani. A rather controversial topic given awareness by the shack in Hampstead and the lady in the van is that of gentrification. Have you considered this in your study? Given awareness by the shack in Hampstead and the lady in the van. You'll have to tell me more about this because I don't know what it is. I'm wondering if it's housing which is left unlived in, but bought out by transnational elites and wealthy people. Is that Ashmin?
Yeah, I mean, no, it's me. I was just going to say, I think we can circle back to those questions maybe at the end of your talk if you want.
Okay, cool.
Yeah, on screen and find out. Cool.
I'm curious about that question, so I look forward to it. All right. Okay, so then from the methodology sort of side of things, I'm really interested in looking at how different clustering methods lead to different results. So one of the sort of unfortunate things in the literature, a lot of the deep clustering methods typically use benchmark data sets. So we're talking MNIST, we're talking CFAR, we're talking fashion MNIST. And it becomes really difficult from an applied sense to grasp, okay, well, what is meaningful within these methods? So I've already spoken about the sort of two-step methods. I'm also investigating a model called Deep Cluster, which my colleague Barbara actually introduced me to. And this adds, essentially what it's doing is it's adding a cluster label loss to the training process. From the reconstruction side, there's the possibility to also then train to reconstruct, which is adding the reconstruction loss. And the various, so typically this sort of Gaussian mixture, VAE, there's hardly used on any applied data sets. But also to begin with, I'll just look at variational autoencoders with a pre-trained, let's say, ResNet or VGG for extracting image features. And just a brief look at what Barbara and I looked at previously, and still have some work to do, is the difference in clusters. So on the left are the 9 clusters used from RMAC, and on the right are the 9 clusters from Deep Cluster. I think what's most interesting is this cluster 8 here from the Deep Cluster, which essentially is taking a bit of everything. And there's a lot more room to investigate whether that is, whether, for example, RMAC just has a lot more noise in. So this cluster 8 becomes, sort of this uncertain noisy cluster, or whether there's something really meaningful about this mix of images. So I've also just written here the mutual information, which is relatively low. And the way in which we sort of thought about looking at, well, what's the difference within the images, is to look at the sum of t-score differences between, as I mentioned earlier, all of those features that were relevant for predicting cluster assignment. So essentially a low sum of t-score differences is indicative of clusters that are more similar. So here cluster 6 and cluster 2, here cluster 2 and cluster 0, etc., and so on and so on. And when looking at what the distribution of those look like, so this is 2 and 0, very similar for building segmentation, very similar for road segmentation, very similar for sky segmentation. And so there's sort of, here maybe there's a bit more discrepancy between cluster 7 and cluster 3. So this is just a way of, one of the ways that we've come up with so far of saying, okay, well, how similar are these clusters given the different methods? And we've got a lot more to look into in terms of comparing different clustering methods. So yeah, deeper analysis, and also to include those other 2 methodological comparisons, which have both reconstruction and reconstruction plus cluster label loss. Okay, so that's sort of part A, and part B is now, so I got also very interested, as I mentioned before, living in London, this very subjective sort of like, how do you experience your neighborhood? Got very interested in subjective experiences, and there was this very cool study in 2014 called Place Polls, which you may have heard of, which essentially collected ratings of people's perceptions of images. So it was done in 2014, sort of the original study, and then it was updated again in 2016, and it included 110,000 images from 162 cities in the world, and they were able, over a period of 3 years, to collect over 1 million comparisons by users, asking them to rate images as which one is more safe, more lively, beautiful, wealthy, depressing, or boring. And here's just an example of images that were predicted on a scale of low to high safety, liveliness, wealth, and beauty. So I was able to get my hands on the 110,000 images, and my goal was to then say, okay, given all of this data which has been collected, can I now predict these perceptions on the London images which I have? And I just used a ResNet, and it was to regress on the Q scores. So after all the comparisons were brought in, they converted them into rankings essentially, and from that derived Q scores, and those I rescaled to be between 0 and 10. Another problem was the distribution of the tails. So I oversampled at the tails in order to be able to get better prediction. And this is just the test split, so 65, 5, 30. I don't know what happened to this graph. Something happened to it. It went for walks. But for safety, liveliness, wealth, and boring, this is just the loss curves for each epoch of the mean squared error. And here you can see what the sort of trend looks like between the ground truth and the prediction, which for safety has the best performance. So safety, essentially, we're plus or minus 1 in essence for predicting safety, whereas it's a lot lower for wealth, boring, beauty, and depressing. And this, so I sort of reasoned that this could be a number of things. It could either be that there weren't enough votes on those images. So that's to say, you know, you need a minimum of 500,000 ratings on these images, which ends up being, I think, about 3 votes each, in order for you to get a good enough in order for you to learn an accurate representation of what safety is being encoded by the users. But on the other hand, it could also be, you know, some things just aren't as well represented, like in a partitionable way in imagery, or subjectively there's a like higher subjectivity of beauty, for example, than there is of safety. So there's a couple of different sort of reasons behind that, but I think it is worthwhile to say there should be a minimum number of ratings to collect something which is to be able to rank all the images in a meaningful way. Okay, so this is just a visual illustration of high safety and low safety. So there's definitely some from the London images once I built the model. So there's definitely something in it which is showing lots of greenery, for example, lots of red as something which turns out to be not so safe, and lack of greenery, fences. So then what I was interested in, if you remember, I said there's 162 cities around the world that were used as an input for the model. So here I'm just looking at a handful of the images included in Place Polls that were rated. So the safety ground truth is in green, whereas the prediction from the model is in red. And the differences shown here have a difference greater than 3. So if I choose 2 images and ask which one is safer, the model will tell you the top middle one is safer. Whereas the people voted bottom right and this is almost second least safe according to what people have voted. So it sort of led me to this question that how transferable are each of these perceptions from city to city? What sort of meaning does safety have when you're talking about London versus safety when you're talking about another city in the world? And also, how does this change based on your demographic? Do users have a different idea of what is safe and what is not safe? And especially from London, as the perspective of somebody that lives here and navigates the city, there's probably ideas of maybe, for example, this alleyway is something which is too narrow and there's not many onlookers, so it sort of gives this perception actually it's not that safe. Because there's various different ways that people might actually interpret it. One of the good things is that PlacePulse has shown already the efficacy of collecting enough ratings. So even though they can be differences in the perceptions, they don't report significant differences across their demographic profile. But again, as I mentioned, it was across these 162 cities. So anyway, what I decided to do was create my own app to ask for perceptions of walkability in London. And walkability became interesting to me because this was during the lockdown. So there was a whole different way of perceiving like your neighborhood. Every time I went out for a walk, I was thinking about where can I go new, where can I go that's pleasant, how can I traverse my neighborhood in a way that's actually enjoyable. And whether that's because of things like knowing that there's a road nearby or knowing the continuity of the road, a lot of it was also made up of like, what does the neighborhood look like to me? So this is not that exciting. This is just sort of the framework in which I built it. I made a blog post about it and put some code on GitHub to talk about how I built the infrastructure. I also sampled the method. So the two big differences between what PlacePulse did and what I'm doing is this sort of like city-specific look into perceptions. And furthermore, I also pre-sampled the images in a way that it shows users images based on the cluster assignment. So I was also going to show users images based on the inferred PlacePulse ratings, but after doing a pilot analysis, it turns out that there wasn't an obvious winner when it came to PlacePulse rating, as I sort of thought there would be, given that those are already perceptions taken from people, which actually adds more motivation to continue and actually collect new ratings, given that there wasn't an obvious winner from the PlacePulse ratings. Also had to do an ethics application with my university. Luckily, none of the data is individual level data, so I'm not subject to GDPR. And we launched in 2021, and I did this sketching event and made the website available on this London Festival of Architecture. So how else am I going to reach people? Luckily, I get to talk at seminars like this, and I have a wonderful audience who would, I'm sure, be very excited to participate in my research. And ultimately, what I'd like to do is isolate areas in the city that are in need of urban renewal, to find those areas in London which are sort of sinks, in which people actually aren't using them as a space to engage with, walk in, experience their city. And hopefully the tool itself can be a template for participatory design within the city. So this is just an example, very straightforward. On which street would you prefer to walk? You get to choose which one, and at the bottom it will also tell you how much this was in agreement with the PlacePulse ratings. Okay, so this is all I wanted to say on my research. So I guess that was part B. So this is final part C, and it's just going to be very brief, where I just share some of the work that we did within the group as a collaboration. So as I mentioned, so this paper is currently in submission. So the title is Do Poverty and Wealth Look the Same in the World Over? A Comparative Study of 12 Cities from 5 High-Income Countries. So this was like a very ambitious data collection project, if I'm honest with you. We had to collect imagery from 12 different cities. So there's 5 cities in the US, 2 Canadian cities, UK, London, and Auckland and Sydney are included in the analysis. And essentially what we're saying is so as well as the images from each of these output areas, we also had to get census statistics. So that was quite a laborious process, emailing people and scraping different websites for as much data as we could. But eventually the results came out and we found that more wealthy neighborhoods look more similar than less wealthy neighborhoods. So that is, neighborhoods on the top deciles actually would transfer better in terms of these learned models than neighborhoods on the bottom deciles. And there's a whole host of different factors which are involved in thinking about why this would be, and especially looking into urban planning and migration, which we haven't actually done in this. This is really just looking at the computational efficacy as opposed to some of the reasons why. But for example, we saw that in the US, models were more transferable within cities in the US, and similarly, models were more transferable within cities in in Canada, so Vancouver and Toronto. So there also being probably some reasoning around urban planning and development, which actually makes sense why neighborhoods are more transferable within a given country. And this is just a visual of what the network looked like. So as I mentioned, VGG, feature extraction with these 4 channels for each of the different inputs, and then looking at predicting each of the deciles. So this was London ground truth versus what happens when you train in London and predict in London, whereas this is London ground truth, what happens when you train in Toronto and predict in London. And so you can see the difference in predictions across each of those different cities. So that was the first project. And the next project, we looked at spatiotemporal characterization of human activity and environment in Accra with citywide image collection and deep learning. So Sierra Clark, another colleague, did a huge field campaign collecting loads of measures of air and noise pollution in Accra. And alongside that also collected imagery as part of the sort of study design. So along with Ricky, we thought about how now could you potentially detect features in the image which are potential contributors to air and noise pollution. And because of the image data set, it was very different from a lot of the object detection data sets which exist already. We had to come up with ways of labeling. Not only are they different, but also the density of people is really high. So we had to get a model to learn how to actually extract features with, what happens when there's a lot of people in the image. And the people are really far back in the image as well. So they're present, but further in the distance. So we used this tool Labelbox, and we got a whole host of keen and excited collaborators to label the images themselves. I think we labeled a subset of 1,500, and from that we were able to train an algorithm. I've forgotten exactly which one, but it's definitely from the Deep Lab TensorFlow model Zoo, and eventually we could see much better predictions in some of the objects in the imagery. So from that, then we could look at the spatial and temporal characterization of the activity. So here's just a few examples: people, two-wheelers, small vehicles, large vehicles, animals, and refuge, and the sort of counts. One of the things which was also interesting is we were interested in novel objects to this specific context. So for example, like minibus taxis that we have, it's the same in Accra, but they're called trotros. So how then could you characterize trotros which have not ever been detected before? So that was sort of this novel object capture within Accra. And so they're currently doing work on looking at the levels of pollution, which Ricky's kind of taking ahead. So how do these objects actually relate to pollution levels? And that is everything. So thank you so much for listening to me, and please visit my website to participate in collecting ratings of walkability in London.
Awesome. Thank you so much, Emily. Okay, I'm going to try and bring Ashmin online to see if she can ask me questions. But in the meantime, maybe you can start by answering the data privacy question. So how do you handle data privacy, and is there anything the ordinary citizen should be thinking about?
It depends which project you're talking about. So the most contentious data privacy issue is around the imagery in Accra, I would say. And we had to go through a process with I'm not the best person because I wasn't part of the survey design, but as far as I'm aware, we had to go through a process with the University of Ghana. The entire data collection was in partnership with the University of Ghana. So the University of Ghana, which then is, in some regulatory framework within Ghana itself, and with the university here and at Imperial, to be allowed to, first of all. But there's massive conversations going on about like how to actually make these images accessible and available to the wider community, because one of the options is to like face blur, but simultaneously, if you have a bit more information, so say for example, what residence the image is capturing, you might actually still be able to identify people if even if you have face blurring taking place. So there's a lot of thought from Ricky and Sarah going into how can those, because it's a really rich data set, but how can they be made available in a way which is private? From the perspective of Google and privacy, I do not mean to wash my hands clean in any way, but simultaneously, Google are dealing with a whole bunch of things in terms of privacy on their side. So users can ask to have images taken down, but the images are available online, they're there essentially. So if they're available from Google's side, then I sort of don't have to jump as many loops to get access to them. And then for the website privacy is that I'm not collecting any private data. So I'm collecting just broad demographic information. I hope that answers the question.
Yeah, 100%. Thanks so much. Okay, it seems like Ashmin is connecting. Let me just see. Let's just give her a moment. There we go. Hi,
thanks for your wonderful talk and study. I was just asking about gentrification. So the references I made was to an Alan Bennett screenplay, which turned into a movie, where there was a woman in a van parked in Camden for some years, and that was taken to task by the social elites in the area, but she'd also been causing problems, with her garbage and so forth. So that's, in terms of gentrification, I think it's completely related to what you're doing. And what is your take on this?
Yeah, interesting. So not being a social scientist and having this full sort of view of all of the factors that are involved within the process of gentrification, I would hope that the method that I'm using and the sort of analysis that I'm doing would be able to detect indicators of change, because the change that I want to see is over the 10-year period. And from my own experience living in London, neighbourhoods can be changed in 5 years. You can see transformation in an entire area. If you think about Aylesbury in Elephant and Castle, like that was just it. Within 10 years, it is a new place completely. So from the analysis that I do, I would want to be able to detect those changes from like the visual perspective, and also the extent of those changes, to say, okay, how far out is this neighborhood becoming something different, and then ground truth those with what the census variables are saying. So how within 10 years, what is the demographic of the people within those neighborhoods? And I guess maybe sort of efficacy is to say, if you want to be measuring changes in neighborhood at a higher temporal frequency, rather than waiting every 10 years, it might be to say, can you use images to understand how neighborhood boundaries are constantly changing and people are being pushed into new places?
Okay, and I suppose a follow-up question would be, did you consider pre- and post-Brexit data in this study?
So I haven't, and I know now the housing market's absolutely mental, which maybe is a combination of Brexit, pandemic, many different factors, Europeans leaving en masse. I'm not you know, because the census was done last year. I filled it in last year. Yeah, I filled it in last year. I don't know how to think about that yet. And I'm even hoping that I'll be able to get access to the census statistics, because I don't know when they're going to release them. But I don't know how to think about what the change will look like given Brexit in terms of the visual layout of the environment.
Okay, great. Thanks so much.
Thank you.
Thanks so much for joining us on screen, Ashmi. Then there's one more question left. So last chance to everyone to get your questions in. So what advice, sort of in honor of Ada Lovelace Day as well, what advice would you give for anyone that has been inspired to work or study in this field?
Interesting. Maybe that it's never too late to learn. You know, I guess I started with my journey in Python at AIMS, African Institute for Mathematical Sciences. Lots of love to that place, in 2017. And ever since then, it's just been like continuous upskilling and learning more. So I suppose just the willingness to see like the long time scale of how long it takes to really grasp things. What other advice? That's a hard question. I think I could probably write like a letter about it, but off the top of my head, I'm not entirely sure what the rest of the advice was. Also just connecting with the community. There's so many powerful resources, other people with incredible skills and opportunities. So that's another huge, for me personally, it's been a huge like positive impact in what I do.
Yeah, 100%. No, I think that's a great answer. Thanks so much. Okay, it does not seem like we have any more questions, so I will just watch that for the next couple of moments. But yeah, I'd like to thank you so much for joining us today, for giving us this very cool talk. Yeah, if everyone can please give Emily a virtual round of applause in the comment section. And also do remember to subscribe to NERV's mailing list and calendar. I will post those links just now. And thank you to all of you for attending, and we will see you again soon. Oh, it seems there's one more question. There we go.
Yeah, I was just reading that. I was going to reply by text. So I'm not using satellite data. I know a lot of people that are, and definitely, especially even in Cape Town, I always forget the name of the Aero something. The startup that uses remote sensing satellite imagery for agritech, basically. Aerobotics, thank you. So there's loads of people doing this sort of work, and one of my colleagues, Barbara, is using satellite imagery for understanding urban development in Accra. So I can very much put you in touch if you're interested in that sort of field, that sort of line of work. Yeah.
Awesome. Okay. Cool. With that, I think that is our event for today. Thank you so much, Emily.
Thank you so much for having me. Awesome.
Cool. Cheers, everyone.